So some of you have requested that I make a tutorial video about how I apply data science to my work. And so in this tutorial, I'm going to do just that. I'm going to show you how I apply data science to the field of Cheminformatics. And in this notebook, it will be a end-to-end machine learning project in Python. And so we will be reproducing a published paper from Delaney, who built a linear regression model for predicting the solubility of molecules. So the solubility of molecules is an important physical-chemical properties for drug discovery as performed by pharmaceutical companies and academia. And so without further ado, let's get started. So the first thing that you want to do is head over to the GitHub of the data professor, click on the code repository, find Python and click on that. And then scroll down to find Cheminformatics predicting solubility, click on it. And then click on the raw link, right click, save link as, and save it into your computer, okay? And if you want to follow along on Google Colab, you can do so. Click on File, Open Notebook. Click on the GitHub tab, type in Data Professor, and then find Cheminformatics, predicting solubility, click on it. But because I already have it open, I'm going to use that. And so here I'm going to clear all of the outputs by click on the edit, clear all outputs. And so we're going to follow this along step by step. And so before beginning, I got the inspiration for this Jupyter notebook from an excellent blog post that I read from Pat Walters. So he is one of the authors of the Deep Learning for the Life Sciences book by O'Reilly. And so the book was about the application of deep learning for predicting various activities and properties in the life sciences, where he briefly discussed in the book about predicting the molecular solubility. But a more in-depth example was provided by his blog post. And so the dataset was downloaded directly from the original paper by John Delaney. Okay, so without further ado, let's have a look at the code. So the first thing that you want to do is you want to install rdkit. And in order to do that, you need to install the Conda. Okay, and the installation of Conda is already described by my previous video. So if you haven't watched it yet, please click on the link above. Okay, so run this cell. And so this cell will install Conda and then followed by the installation of the rdkit. And so this should take a while because rdkit is a pretty big package. Okay, and now we have rdkit installed already. And so as originally described, the dataset for the solubility of molecule was derived from this link, and the original paper is linked here. And so the data was coming from this paper published in the year 2004. And so in this paper, they predicted the log S value, the solubility value of compounds. And so the supplementary file is right here if you click on this link. Or from the original article, it is in the supplementary right here in the text. So if you click on it, it will be the exact same files that we have in here. So we're going to go ahead and download the data. Okay, and then we're going to use Pandas to load in the data set. Oh, it was temporarily unavailable. So let's try again. Okay, and so it's still not available. So let me do this. Let me download this and then I'll upload it to the GitHub of Data Professor. So if that doesn't work, then we'll use this directly from the GitHub then. Okay, and then I'll rename this. Oh, I have to import Pandas and then I'll read it in again. Okay, now it works. So feel free to use the version that I uploaded to the GitHub just for backup purposes. So as you can see that it didn't work on Colab, but then it worked on my local computer, okay? Okay, so let's continue and read in the dataset, and which we have already done, and let's print it out. And so we can see that there are a total of 4 columns, and the first column will be the compound name, and the second is the actual value, the experimental value for the log S, the solubility, and then the third column is the predicted value from their study, and then the fourth column are the SMILES notation. And so in the field of cheminformatics, SMILES notation represents the acronym for Simplified Molecular Input Line Entry System, and it is essentially compressing the chemical structure information into a one-dimensional form. And so the one-dimensional form is shown here. For example, F would correspond to fluorine, C would correspond to carbon, N would correspond to nitrogen, O would be oxygen, equal sign would be double bond, okay? And the parenthesis will tell it that it is attached to a particular atom. Okay, and so we're going to use the SMILES column, and so we're going to type in SOL, which is the name of the data frame, dot SMILES. And so we see the SMILES column, and it has a total of 1,144 rows or compounds. And so if we want the first SMILES from this list, we're going to use the slice function. So we're going to type in so.SMILES bracket and then the number 0 for the first row. And so if we have 1 here, it will be the second compound. And if we have 2, it will be the third compound, etc. And in order to allow the rdkit to comprehend the information of the chemical structure, we're going to need to read it in to rdkit by converting the SMILES notation, which is an ASCII text, into a rdkit object. So we're going to use the chem submodule dot move from SMILES function. So what this essentially does is convert the SMILES notation from the ASCII form into the object. Okay, and so we see that the object is right here, and it contains this unique ID, and it will be exactly the same as using the string of the SMILES notation. As I have shown earlier, when I type in so.SMILES bracket 0, it will be giving this string as the output. So you can also specify the SMILES string directly. So either run this line or this line, and you will see the same thing, that the molecule will be generated and they will have a unique object ID. Okay, and then we're going to do this further by assigning this rdkit object into the variable m. And then we're going to use some function to see how many number of atoms does it have. So we're going to use m, which represents the rdkit object for the molecule, and then dot the function get number of atoms. And so we're going to see that this compound has 6 atoms. Okay, so what this essentially does is it computes the number of atoms in the molecule. And so we're going to continue with calculating the molecular descriptors using the rdkit. And so we can do this in the chem submodule. So from rdkit, import chem. Okay, and so I'm going to show you 2 methods of doing it, and it is essentially the same thing. The first method will be more lengthy. We're going to use the for loop in the original form, and the method 2 will be the for loop, but in a more concise way. As you can see, it is in the one line. Okay, and so using either method 1 or 2, it will produce the same output. So let's try with method 1. And so what this essentially does is, first it will create an empty list, and then for each of the SMILES notation in the so.SMILES list, it will iterate for each element in the list of so.SMILES. It will convert the element into an rdkit object. And then it will assign the rdkit object of the molecule into the mole variable. And then it will append this mole object into the mole list variable list here that you see. So it will start from a empty list, and with each iteration, each molecule from the so.SMILES will be converted into the rdkit object of the molecule, and it will be appended to the mole list. So this thing will grow. Okay, and let's have a look. And so it has a length of 1,144, which is the same number as the number of compounds. And so let's show only the first 5. And so it will look like this. So you see that there are 5 rdkit objects here. Okay, and let's do it with method 2. And we're going to call it a slightly different name, molelist2. And 1,144 compounds, and the object as usual. Okay, so now we have already converted the SMILES notation from the text form into the rdkit object form of the molecule. And now we're going to continue with using the rdkit object molecule in order to compute the descriptor. And the original study by Delaney, he made use of 4 molecular descriptors comprising of the octanol water partition coefficient, which is the ratio between the solubility of a molecule in octanol and water. And so the log P will be one of the descriptor to predict the log S, which is the solubility in water. And the second descriptor is the molecular weight. And so the molecular weight is the summation of the individual atomic weight. And the third variable is the number of rotatable bonds. So let me show you this. This is a molecule, and the rotatable bond will mean like this. How many bonds can be rotated? As you can see, the atoms will move because I rotate the bond. And if I rotate this bond right here in the gray color, if I rotate it, notice that the atoms are moving. See, the red represents the oxygen, black represents carbon, white represents the hydrogen. And so this bond is rotatable. Okay, this bond is also rotatable. Okay, and this bond is rotatable right here. I rotate it. But this double bond, you will see it here. This double bond, it has 1, 2. It's a double bond. It cannot be rotated. Okay? Okay, let's continue. And so the fourth descriptor is the aromatic proportion, and this represents the ratio between the number of aromatic atoms to the total number of heavy atoms. And so rdkit can readily compute the first three descriptor, and the fourth descriptor, we're going to have to compute that manually. And so how are we going to do this exactly? We're going to just manually compute the ratio between the number of aromatic atoms and the number of heavy atoms. So just a simple division. But we're going to have to manually compute each of these descriptors separately and then compute the ratio. Okay, and so here we're going to compute the three descriptors, log P, molecular weight, and the rotatable bonds. And so we're going to use the rdkit.chem module, and we're going to import the descriptor function. And so please note that this block of code was inspired by this CodeOcean project here for the generating of the descriptors using the rdkit. And so the first block here that you see in the function, it will essentially do the same thing as I have already discussed up here in method 1 or method 2, whereby it will create an empty list of the molecule and then read each SMILES text and then convert that into the rdkit object and append it one by one into the mole list. Okay, and then here we're going to just change the name mole list to become mole data. So essentially it will convert the SMILES text into the rdkit object. And then after that, it will compute the 4 descriptors using the mole object. And so when the descriptors have been computed, it will convert it into the NumPy array, and then it will dump it into the data frame using Pandas. And so it will return the Pandas data frame. Okay, so let's run this block of code here. And so let's generate the descriptor and put it into the new data frame variable. Okay, I have to define the modules. Run it again. Alright, so the descriptors for the first 3 are computed successfully. And now let's proceed with computing the fourth descriptor, the aromatic proportion. So let's show you an example of how we compute this for a single molecule. So for the M variable, it's going to be the SMILES of the molecule. And then we're going to convert this into a rdkit mole object. And so for the molecular object here, we're going to retrieve all of the atom from the molecule. And then for each atom, we're going to determine whether it is aromatic or not aromatic. And if it is aromatic, it will become true. And if it is not aromatic, it will be false. Okay, and then we're going to count the number of true. And so that will give us the number of aromatic atoms. Okay, true and false. So true will be the number of aromatic atoms. And so we're going to count all the true here. And so here, it will be the summation here. So let's define this function. And then let's determine the aromatic atoms in the molecule. And then we have 19. So the molecule up here, there is 19 aromatic atoms, meaning that the atoms are belonging to the aromatic rings. Okay, and so we're going to do this computing of the aromatic atoms for the entire data set. So we have the number of aromatic atoms for each of the molecule. Okay, and we're going to do the same thing using this example for a single molecule, and then we're going to use the descriptors.heavy-atom-count in order to get the number of heavy atoms. 19. And so the previous number, aromatic atom, is 19, and this heavy atom count is 34. So 19 divided by 34 will give us the ratio of the atomic proportion. So we're going to compute the heavy atom count for the entire data set. And so we're going to take in these two variables, the aromatic atoms and the heavy atom count, and then we're going to divide them. And so as you see, 19 divided by 34, the aromatic atoms divided by the heavy atom count will be 0.5588. And so we're going to do this for the entire data set. And so here you go. The aromatic proportion descriptor has already been calculated. And so we're going to combine the two data frames together, the DF, which contains the 3 molecular descriptor, and the DF aromatic proportion, which is the 4th molecular descriptor. So we're going to combine that using pd.concat. And then as argument, we're going to have it in the bracket, the first data frame, which is DF, and then the second data frame, which is DF DESC aromatic proportion. And then we're going to set axis to be 1 because we're going to take the 2 data frame and join them side by side. And then we're going to have 4 columns. And so this will represent the X matrix. And so we will use the X matrix in scikit-learn for the model building in order to predict the Y matrix, which is the log S, or the solubility of the molecule. Okay, so it is this column, the second column. And so we're going to select it by using the iloc function and then colon and then comma 1 because we want to select only the second column. And we're going to select this by the index number. Okay, let's do that. And then we have the second column selected. Okay, and now we already have the data matrices of X and Y ready. And now let's proceed with data splitting. And then we're going to set the ratio to become 80-20. And then for the data splitting, we're going to use the train test split from the scikit-learn model selection submodule. Okay, and here we use X and Y as the input argument and the test size to be 0.2 because we want the test to be 20%. And so the 80% will be the train set. And so here we're going to build a simple linear regression model, and we're going to assign model equal to linear model dot linear regression. And then we're going to have the model built using model.fit. And so the model.fit will use the X variables and the Y variable for model training. And now that we have the trained model, we will apply it to make the prediction on the X train and the X test for comparative purpose. Okay, and then we're going to run the model. And then we're going to apply the model for the prediction now. And so the first prediction we're doing here is on the X train dataset. And so this is for comparative purposes. And then we're going to print out the coefficients and the intercept, and then the metrics such as MSE and the coefficient of determination, which is essentially the Pearson's correlation coefficient squared. And then now we're going to apply the model on the X test, the 20%. Okay, and we get the R square for the train set to be 0.77 and the R square for the testing set to be 0.75. And so let's now have a look at the linear regression equation. And so the equation provided by the work of Delaney provides the following equation. Log S equal to the y-intercept, 0.16, minus 0.63, C log P, minus 0.0062 molecular weight, plus 0.066 RB minus 0.74 AP. Okay, so we see that there are the 4 descriptors, and then the number in front are the regression coefficients, which are right here. And then the y-intercept is right here. And so let's compare that with the reproduction by Pat Walters, and it is right here. 0.26 for the y-intercept, 0.74 for the log P, 0.0066 molecular weight, 0.0034 for the RB, and 0.42 for the AP. Okay, and notice the positive and negative signs in front as well. And so our notebook reproduction provide the following equation. So at first glance, it seemed that our model RB variable had a different sign for the regression coefficient. But notice that this is for the train set. And so the 2 studies here were based on the full data set. And so we also compute the regression equation for the full data set as well below here. And so we see that there is reasonably similar for the 2 equation by Pat Walters and the one by our notebook, only with slight deviation for the rotatable bonds. But the other are exactly the same, 0.26, 0.74, 0.0032, but this is 0.0034, and the AP is exactly the same, 0.42. Okay, and so here we use the full data set to build the model. And so we're going to run it. And so notice that the equation that we have up here was provided by the following block of code. So as always, we use the modular string format to display the equation by taking in the variables as shown here after the percent operator. And so the same equation can be generated using the following block of code. And so the block of codes here are slightly easier to read because it breaks down each component into the individual variable, intercept, log P, MW, RB, and AP. And then we use the modulo operator. And then we're going to print it out by fusing together all of these. And then we get the equation. Okay. So these two blocks of code is essentially the same as this block of code here. Okay. And then the equation that we got for the full data set right here was derived from the run here. So we're just going to run it. Okay, and this equation was pasted above. Okay, and so let's have a quick look at how we can plot the scatter plot of the predicted value versus the experimental value. And before doing that, let's do a quick check of the variable dimensions. And so for the training set, we have 915 compounds. And the test set, we have 229. And let's make the scatter plot using matplotlib. And so we have this to plot. And we're stacking it vertically, whereas in the following block of code, we have it horizontally. Okay, and so let's go into detail here. And so notice that we have two blocks of code right here. The first block of code represents the first plot. And then the second block of code here represents the second plot. Okay. And then notice that here in plt.figure, we define it to be the dimension of the figure. So 5 is the width. And so 11 is the length. So we see that the width is 5 and the length is 11 to accommodate two plots. And in here, we define the subplot 1 to be 211 and the subplot 2 to be 212. And 2, the first number here, 2, corresponds to 2 rows. And then the second value, 1, is 1 column. And then the third value here, 1 is the first plot and 2 is the second plot. Okay. And so for the input argument of x and y in the plot scatter function, we're going to use the y train to be the x and then the y predicted of the training set to be the y. And then we define the color in C argument here. And then we make each of the data samples dot here to be having a transparency of 0.3. And then the trend line, which we see as red color, is provided by this block of code here. And so we're using the numpy polyfit function. And so the details of this was taken from the Stack Overflow here. And so we're going to plot the Y label and the X label correspondingly. As you can see here, we plotted once, not here, but only at the bottom and to the left. Okay. And now let's jump on to the horizontal plot. So the concept is exactly the same, but notice that the subplot has the numbers rearranged a little bit. So it's now 1, 2, 1. Before, it was 2, 1, 1 and 2, 1, 2. Because 2 was 2 rows, 1 is 1 column, and then we have 1 and 2, which is the plot 1, plot 2. But in here, we have only 1 row. So it starts with 1. And then the 2 here corresponds to 2 columns. And then we have 1 and 2, which corresponds to plot 1, plot 2. Okay, and everything else is the same, but notice that the X and Y label here is slightly shifted. In the above, we have the X label to be occurring 1 time, and we have Y label occurring 2 times. Okay, here, X label is occurring for 1 time for the bottom plot, and the Y label is occurring 2 times. 1, 2, because we have here 1, 2. And for the horizontal plot, because we want to display the X label twice, we're going to have the X label 2 times in the code. And then we're going to have only the Y label once. Okay. And then plt.show to show the figure. And then plt.savefig to save the file into your working directory. Okay. And so ls list, and then we're going to see the created PDF and PNG files. Okay. So congratulations, you have now built your first Cheminformatics project by predicting the solubility of molecules. And so here we reproduce the work by Delaney, which he performed back in 2004. And so we have reproduced this using Python, scikit-learn, and we visualize the distribution of the data points using the matplotlib. So please feel free to modify this to be a different data set, and as always, upload it to your GitHub and expand your data science portfolio, because the best way to learn data science is by doing data science. And so please enjoy the journey. Thank you for watching. Please like, subscribe, and share, and I'll see you in the next one. But in the meantime, please check out these videos.